Hey everyone, and welcome. Grab a seat, get comfortable. Consider this your masterclass in cosmic extremes. I am so incredibly excited to have you all in class today for this explainer, because we're tackling one of the most misunderstood, awe-inspiring, and frankly terrifying phenomenon in the entire universe. Today, we are going to completely dismantle those sci-fi myths you've grown up with and replace them with the actual mind-bending physics of black holes. We're going to journey from the mathematical predictions of the past all the way to the breathtaking photographs of the present. Get ready, because the truth of our universe is just so much stranger and way more fascinating than fiction.
Here is our syllabus for today's explainer. We've got the cosmic vacuum myth, anatomy and formation, space-time and spaghettification, seeing the invisible, and finally, shaping our galaxies. Okay, let's just dive right into this.
Section 1, the cosmic vacuum myth, separating sci-fi from science. Now, before we can really learn what a black hole actually is, I need you to just forget everything Hollywood has taught you about them.
I want to pose this question directly to the class. Are black holes actually cosmic vacuum cleaners? It's kind of the most common visual we have, right? You know, a giant whirlpool in space, just violently sucking up every planet and star in its path? Well, the answer is a resounding no. They absolutely do not roam around the universe actively slurping up galaxies. Think about it this way. If you were to replace our sun right now with a black hole of the exact same mass, Earth wouldn't get sucked in. No way. We would continue to orbit it exactly as we do now. I mean, it would be a very cold, incredibly dark Tuesday, but our orbit wouldn't change. The gravity remains the exact same. It's just the density that changes.
So if it's not a giant vacuum, what is it? Well, NASA provides this beautiful, simple definition. A black hole is a region where gravity wins so completely that nothing, not even light, can escape. I really want you to focus on that phrase, gravity wins completely. In this epic cosmic tug-of-war between the outward pressure of energy and the inward pull of gravity, gravity is the ultimate victor. It pulls so intensely because an enormous amount of matter has been squeezed into an unbelievably tiny space. And since no light can get out, they are literally completely invisible to the naked eye.
Moving right along to Section 2, anatomy and formation, building a behemoth. So how exactly do you build a gravitational trap where light itself can't escape?
If we strip a black hole down to its core anatomy, it reveals two essential features. First, right smack in the center, you have the singularity. This is where all that mass is compressed into a single, infinitely dense point. All of our current laws of physics, they just completely break down right there. And surrounding that singularity is the event horizon. Now, it is absolutely crucial for you to understand that the event horizon is not a physical, solid surface you could, knock on. It's a boundary. It is the ultimate point of no return. Once you cross the event horizon, the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, well, nothing can escape.
So how are these incredible structures born? It usually starts with a truly massive star. For millions of years, nuclear fusion pushes outward while gravity pulls inward, and that creates a perfect balance. But what happens when the fuel runs out? That outward pressure just disappears. The star collapses under its own immense gravity in literally a fraction of a second. This incredibly violent stellar collapse creates a massive supernova explosion, leaving behind the heavily compressed core, which we call a stellar black hole. Over billions of years, these stellar black holes can feed on surrounding gas and dust, or they can even merge with other black holes, eventually growing into supermassive giants.
Now, what's really interesting here is the sheer scale of these objects. NASA recognizes three distinct sizes: stellar, intermediate, and supermassive. Stellar black holes are born directly from dying stars, and they pack anywhere from a few to tens of times the mass of our sun into a space about the size of a single city. Then we have the elusive intermediate black holes, kind of the missing link in cosmic evolution. And meanwhile, supermassive black holes pack millions to billions of times the mass of our sun. To put that into perspective, the size difference is literally like comparing a single grain of sand to Mount Everest. It's just staggering.
Section 3, spacetime and spaghettification, physics at the edge. Okay, prepare yourselves, because the physics here get absolutely mind-bending.
Let's imagine you were to travel toward an event horizon. You'd experience two extreme phenomena, both of which are fully validated by Einstein's theory of general relativity. First up is time dilation. See, gravity bends space, sure, but it also bends time. The closer you get to the black hole, the slower time moves for you relative to someone observing you from far away. To you, your watch ticks normally. But to an outside observer, you'd appear to slow down to a completely frozen halt. And this brilliantly sets up the second point, spaghettification. It's driven by extreme tidal forces. Because the gravity is so intensely concentrated, if you fell in feet first, the gravitational pull on your feet would be vastly stronger than the pull on your head. You would be stretched vertically and compressed horizontally into a long, thin strand of atoms. You would, quite literally, be turned into a piece of cosmic spaghetti. What a way to go, right?
Section 4. Seeing the Invisible. A Brief History of Discovery. So, if nothing, not even light, can escape, how on earth do you take a picture of a shadow in the dark?
For an entire century, black holes were basically just math. The foundations of Einstein's general relativity predicted them. But get this, even Einstein himself doubted they could actually exist in reality. Scientists spent decades observing the way stars and gas behaved around invisible, incredibly heavy objects, carefully piecing together indirect evidence. But then came the absolute breakthrough. In 2019, an international collaboration called the Event Horizon Telescope linked radio observatories worldwide to create a virtual Earth-sized telescope. Through the incredible power of interferometry, they captured the very first direct image of a black hole's shadow. This was M87 star, a supermassive black hole 55 million light-years away. It looked like this glowing, fiery donut of plasma surrounding a total abyss. And they didn't stop there. In 2022, they released an image of Sagittarius A star, the supermassive black hole sitting at the very center of our own Milky Way galaxy. We finally photographed the unphotographable.
Which brings us to Section 5, Shaping Our Galaxies, the Ultimate Architects. How does all of this extreme physics actually impact the universe at large? So, the crucial point is this ultimate paradigm shift. Honestly, if you remember one thing from class today, make it this. Black holes are not the cosmic destroyers we once thought they were. Astronomers worldwide now recognize them as fundamental engines of galaxy formation. Almost every large galaxy, including our own, has a supermassive black hole anchoring its center. The massive energetic jets and winds they produce when they feed, they actually push gas around, literally turning star formation on and off. They are the grand architects of the cosmos, regulating the growth and evolution of the galaxies they inhabit. They don't just destroy, they dictate creation.
As we wrap up today's explainer, I really want to leave you with a provocative thought to chew on. If supermassive black holes are the architects of galaxies, shaping the stars and the cosmos around them, what does that mean for the future of our own Milky Way? Sagittarius A is sitting right there in our galactic center, quietly shaping our destiny over billions of years. So keep asking questions, keep looking up, and never stop wondering about the immense, invisible forces that hold our whole universe together. Thank you so much for joining me in class today, and I'll catch you for the next explainer.